Section 1 of a packet dealing with simple machines looks at the lever. We talked about a couple different classes of levers, first, second, and third. So if we're looking at a first class lever, we could think of something like a seesaw or a teeter-totter, whatever you want to call it in a park, where someone can sit here, someone can sit here, so we have a a resistance on one side and an effort on other, and fulcrum in the center. We're looking at a second class lever. What we could use as an example there would be something like a wheelbarrow. So here are the arms that extend out, and we can think of the wheel as a fulcrum, and then also we can think of the load or all the stuff sitting in the wheelbarrow as a resistance, which is working its way down. And then you would be out here applying the effort, trying to lift it up. And then if we have a third class lever, that could be something like a shovel. So if you think about you standing there, with a snow shovel, we could think of the fulcrum kind of being near your body, and we can think of the resistance out here at the end that you're trying to lift up, and then we can think of this as the effort that you're applying with your arm and your bicep, trying to pull up the snow or dirt or whatever you might be shoveling. Taking a look at some of the problems related to levers. Number one, for example, it gives you some information here. It says a first class lever, so we know that might look something similar to a seesaw, so something similar to that. And it says that there is 50 pounds of resistance, so F sub R is going to be 50 pounds. And then what we're going to have to find out eventually is the distance of the resistance, or d sub r. What we're told is that on this side, the distance of the effort is 4 feet, and then also the force of the effort, which would be out here, or on this far side, is 15 pounds. Let's go ahead and plug that in. Remember that in these formulas for moments and rotation dealing with levers, is that the side with the resistance has to be equal to the side of the effort. So that should take you through the first couple problems. Then if we move on to number 4, what we're going to notice is that it's a similar application, but now we're talking about a wheelbarrow, so a second class lever. If we think about that orientation or where it's located, the following would be true. That the fulcrum is kind of out by the wheel, and then it's telling us that the overall length is about 5 feet. Okay, and then also this way we'd have F sub E, or the force of the effort. That's where you'd be lifting this thing up. We also know that the force of the resistance, or F sub R, is 200 pounds. And that's going to be located right here. Think of that kind of as the bucket of the wheelbarrow. And the information provides us that that's located 2 feet over from the fulcrum. So that is information you can use to help you kind of work through that problem, and hopefully that helps you out. Moving on to the last chunk. This deals with a third class lever. And now, similar to a shovel, there's also a tweezers here, and we have the fulcrum here, and then we have the effort being applied in the center. I think we all know what a tweezers is and kind of how that works, and it says that that's equal to 1 pound. 1 pound. And then also the overall length of it is 4 inches, and the force of the resistance, which would be going back this way, or F sub R, is 1/5 of a pound. So essentially what it's saying is that if more than 0.2 pounds or 1/5 of a pound is applied, this lever could break off, and therefore the system isn't super useful or helpful. And what we need to find is the distance in here, d sub E, the distance of the effort. That should take you through questions 7, 8, and 9. Hopefully this is helpful related to first, second, and third class levers.